read it?
It's something. It's not super.
I mean, I could probably find it here somewhere. What section is this? Is this 2.2? Let me see if I have that. Give me a sec. Did I copy this here? That's not it. Oh, here. Is this it? Ah, yeah, this is it. 19. Oh, yeah. Okay. Yeah, let's do this. That looks like fun, doesn't it? Who did this? Yeah, you're right. Okay. So no, it's not that bad. So presumably, since this is separable, presumably you can separate the variables. That's the key. Is since this is in the separable equation category. So what I'd suggest you do is use whatever tools you have in your head to factor these two equations. So we have, I can factor by grouping, probably that would be the easiest thing to do. So I'm going to factor an x out of the first two terms of each of these, numerator and denominator, and then I will factor, let's see, 4, yeah, 4 out of the second two terms for this second one. There we go. So there's my factor by grouping. And then let me just do one more step, and then we will actually do the solving of the equation. So let's see, this is going to be x minus 1 times y plus 3 over x plus 4 times y minus 2. So that's not what was problematic. It was the actual solving. Give me a sec. I'm going to copy. Whoa, it's just moving around of its own free will. Copy this. Copy. Okay. Let me go down, or here, I'll just switch over to switch back to here. There. 19. So 19 distills down to this. dy over dx is equal to this. And now, yes, you can separate this thing. Not too bad. So dy over, well, here. Maybe I'll do it this way. And you let me know if this is too much in one step. There. How's that look? All right. So, and then we're at an impasse. Is that the issue here? Okay, so I'll remind you how to do equations like this. So these are, let's see, they're really, and it's going to sound bad, but they're really simple. Partial fraction, wait. Yeah, these are rational equations. So I don't know if you remember the pain of doing partial fractions in calculus 2. You've blocked it out of your memory. It's okay. Okay, we'll review when we need to. We'll review. But back when you did partial fractions in Calc 2, you learned how to deal with basically quotients, rational functions. These are rational functions. They should succumb to the techniques that we learned back then. But let's not go there yet. We can eventually. There's an easier way. So just partial fractions, look it up. Calc 2, rational functions. You'll figure it out. But here, let me show you an easier way. And that is that what the problem here in both cases is that you have a y and you have a number. If you only had one of these two things, I think you could do this. But having both of them is the problem. So let's get rid of one of them. I'm going to get rid of the y. The way I'm going to do this is I'm going to change this to y plus 3 minus 3 minus 2. Now, I know you think I've just pulled that out of thin air, but you might be able to see the reason why I chose y plus 3. So this and this are the same fraction, right? And I realize that you might not have known to do this, but this is all in service of trying to figure out what the antiderivative of this thing is. And sometimes you have to manipulate things algebraically. I'll deal with the right-hand side in a minute. Let me just show you where this is going. You probably can see where it's going, but just in case, I have y plus 3 minus 5 over y plus 3. And then, of course, you can see that this, hopefully you can see that this separates into the two fractions. And then the rest of this is pretty straightforward. So then this is going to be 1 minus 5 over y plus 3, and you can all integrate that. Don't worry, I'll do it for you, but hopefully you can. So let me back up, because that might have felt like magic, but there's no hidden card. I'm not doing any sleight of hand. The only thing that is at all tricky is this little algebraic trick that mathematicians are famous for, and that is you can add and subtract a number with impunity. Do it with all you want. You can add and subtract 1,000 if you want, but here I just add and subtract 3 because it's helpful for doing this simplification. So if you can understand that, then the rest of this is almost trivial, but we'll all finish it. Don't worry. Well, I just want to make sure that you're happy, or maybe at least not too sad about this. So I'll give you a minute to let it settle in. Okay, so let's see where we are. Now that we've got that settled, I'm going to do basically the same thing on the right-hand side. It's almost the same idea. I want x plus 4 on the top, and so I'm just going to subtract 4. And there you go. And then this becomes x plus 4 over x plus 4 minus 5 over x plus 4. And then this becomes 1 minus 5 over x plus 4. And so this is the integral of 1 minus 5 over x plus 4. That's a 4. Okay, now let's integrate these things. Integral of 1, yeah, easy, y. The integral of 5 over y plus 3. Hopefully this isn't too surprising. So that's, so this is, I'm technically using u substitution, but I don't want to write all the u's down. So if you really need to, you can use u substitution, or you can say, wait a minute, I recognize this. It's going to be, anytime you have 1 over a linear term, you can just, integral is going to be a natural log. And so then you just have to make sure that things match up. Through the derivative of this, you do get this. So, but you could do u substitution if it makes you feel better. Just going to take more time. Same thing goes with the right-hand side. You can see what this is going to look like now. X minus 5 natural log of x plus 4. And then that's plus c. Let's box this up. Wait, do we have an initial condition? Or is it just a... Yeah, there's no solving of this. I'm not going to solve this. So it's either initial condition or we're done. Let me go back. Come on. There it is. Let's see. No initial condition. We're just supposed to solve. Yeah. So anyway, that's where that one was going. Let me go back. I'll put it back up there, and then we'll see if you have further concerns. This is 19. So I'll give you a minute. I know it's a lot to take in. All right. So what else from this homework do we need to figure out how to do the antiderivative for? Oh yeah. What do you think, Andrew? 29. We had to do 29. It was just 19, wasn't it? Let's find out. 29. This one has an initial condition, so we're going to get done with this and then to do the initial condition. Okay, so, yes. Why did I assign that one? Yeah, I mean, I know what I see. I see the problem. It's okay. We'll do it. Okay, yeah, let's see what happens with this. I'll do it since, no, I signed it, so I'm going to do it. Give me a sec here. Why is this doing this? Okay, so it's going to be y e to the negative x. Here, I'll just copy this. Give me a sec. Okay. Whoops, paste. What? Why did it do that? Well, there it is. I didn't mean for it to come in like that. Okay, so here's your equation. or your differential equation. And so let's just go through blindly. I mean, I know exactly what's going to happen and why it is that you're asking about this, but let's just go ahead and blindly do it. And when we get stuck, we'll talk about how to deal with the stuckness. Okay, so we have, let's see, 1 over y dy is equal to e to the negative x squared dx. So far, so good. This is what you would expect. And then we're going to integrate both sides. Natural log. There's the problem, isn't it? We have this integral of e to the negative x squared dx that we're going to run into problems with. So how are we going to do this? Well, the way that we're going to deal with this is we're going to use this initial condition to express this integral as a definite integral. So here's the idea. Y of 4 is equal to 1. So what I'm going to do is I'm going to do something like this. Natural log of y is equal to the integral from, we'll go from 4 to x of e to the negative x squared dx. So let's see what happens when we plug in the number 4, just so that you can see how this shakes out. It says y of 4 should equal 1. And it's always, you want to double check these things. So let me just go ahead and plug this in. Y of 4 is equal to 1. What that means is that, oh, I'm sorry. Sorry, my notation is bad. Let me just fix this. And I'll try to explain. So anytime you need to express a definite integral or an integral that doesn't have an elementary function antiderivative, you can do so by using just the definite integral like this. What we're saying is that we want to do the evaluate the integral from 4 to x. And I had to change the x to a t here because you can't have the same letter as one of your limits as you do here. But this, using the fundamental theorem of calculus, is the same. This is one of the, there's two forms, and I forget if it's the first or the second form, says that this would be the equivalent to dealing with that initial condition. So now let's just see what happens, just to prove that everything's kosher here. When you plug x in equals 4 into this, you get the integral from 4 to 4 of e to the negative t squared, which is equal to 0. And on the left side, you get the natural log of 1, which is also 0. So this works out. It has that same initial condition. And I could even write this like this, that y is equal to plus or minus e to the integral of 4 to x of e to the negative t squared dt. And I know that this is so ugly to you. I guess I want to be clear. This will be not the, it'll be the positive branch, not the negative branch. The reason being that the initial condition is positive. So we're on the positive, not the negative branch. But notice that this fits everything. It fits the differential equation. It also fits the initial condition. Everything works. And it feels bad because you're used to having actual functions as your answers, not integrals. But in a pinch, you can use an integral as your answer. And this is what, especially in situations like this where there is no elementary function antiderivative. So that, I don't know why I would have assigned that, but I did apparently. Yeah. Sorry about that. Okay, so what else do we need to look at from separable? 41? Is this the same deal? Tell me no. Wait, that's not what am I doing? Oh, here we go. This is what I'm doing. Differential equations. 41. Ah, here we go. Down here. There we go. So what's this? Oh, okay. We're supposed to plot the curve. Okay, well. Oh, yeah. That's right. Yeah, this illustrates the, yeah. So all this was supposed to do was to illustrate the fact that small changes. Differential equations are really where you start seeing the so-called butterfly effect. I don't know if you've heard of this idea that if a butterfly flaps its wings in Africa, it can result in a hurricane 3 weeks later in Brazil or something. So just this idea that weather is, the way you model weather is differential equations, and differential equations tend to have the tendency to have, when you have a small change on the input, the output can have a huge change, huge difference. So that's what this is supposed to illustrate. So I guess the problem child is 41. 42 would be a similar problem, wouldn't it? So, so let's see how we're going to solve this one. Let's see, I just assumed looking at it that it would be fine because these two are fine, right? Those aren't a problem because you can just do the integral. Let me see if I can do this for you. So this is going to be 1 over y minus 1 quantity squared plus 0.01 dy is equal to dx. So why don't we do this? Yes, you're going to love this. So so here, we're going to do this. Now, the right-hand side, I assume no one has a problem with. Here, in fact, I'm going to switch back so I have room to do this. Just a minute. Give me a sec. This is the problem right here. Plus, it's a plus there, isn't it? Dx, dy. Okay, so there's the problem. Yeah, you're going to, well, some of you will find this humorous because of my stated favorite function. But here is, or favorite derivative or integral. So here's the u substitution that I would use. So I end up with 1 over u squared plus 0.01 dy. Then the 0.01 is going to be problematic for me, and so I'm going to have to write this like this. 1 over u squared plus 1 over 100. That's what 0.01 is. I'm just doing this in stages. I could have done it in one substitution right up front, but I didn't want to scare you. And so then this is going to be 100 over 100 u squared plus 1. Essentially, all I've done there is I've just rewritten this by multiplying the top and bottom of this fraction by 100. So you get that? Almost done now. You probably can see what's going to happen, but I need to make one more substitution. So if you're going to do a double substitution, instead of u, we'll use double u. And my w will equal 10u. dw is going to be 10 du. And so this thing, let me just rewrite it really quick before we do the substitution. Sorry, this is du here, isn't it? That should have been a du. Yeah, all the way up here, it should have been a du. Okay, so anyway, I'll put 10 du over here. So I'm going to take my 100 that's in the numerator and separate it. And then in the denominator, this is 10u quantity squared plus 1. And so then this ends up being 1 over w squared plus 1 dw. And just to make it super clear, 1 over w squared plus 1 dw. So there it is. What is this antiderivative? Yeah, arctan. So arctan of w. And then you have to go and substitute back in all the junk that you had to get to this stage. So it'd be 10 arctan of w, and the w was 10u, and then the u was y minus 1. So apparently this is 10 arctan of 10 y minus 1. There. So that would be the left side. So yeah, so and just to illustrate what it is that this particular set of, they'll keep changing the wrong thing here. What this is trying to illustrate is with the first two, so let's just walk through these. That one you get, so that one you end up with just 1 over y minus 1, I think is the negative 1 over y minus 1. It's all over here, like when you divide. This will also be negative 1 over y minus 1 on the left side. This one, you get an arctangent on the left side. And this one, little bit of a pain. Did you have to do this one? Okay, yeah. This one you end up with a couple of natural logs. So on the left side, which I think could be done using, uh, nah, it might be like a arc hyperbolic cosine or something, but yeah, it's a couple of natural logs is what this ends up being. So this very small difference in the statement of the problem ends up creating a huge difference in the solution. So this ends up being like this: 1 over y minus 1 is equal to x. This one ends up being arctan of 10y minus 1 is equal to x, something like this. I guess there's a 10 in here. This one ends up being, uh, I don't know, this is like 10. Yeah, don't quote me on this. Y plus 1 minus 10 ln of y minus 1 is equal to x, all because of that little number there. It's such a small number, 1/100th, hardly anything. So that's what that was trying to illustrate. And if you were to graph these look very different. Arctangent looks like a tangent on its side. Natural log, you know what that looks like. It's a nice curve. Although I suppose since I've got two of them, it's going to be, if you solved for this explicitly, we would get some sort of exponential. And that would be a tangent if you solved for it. And I don't know about that thing. Well, that's going to be simple. Y minus 1, 1 over x, a hyperbola of some sort. Like y minus 1 is 1 over x. Yeah, y is equal to negative 1 over x plus 1. Yeah, so that's just this curve. It's got a asymptote. Yeah, so the long range behavior of these 4 or 3 things is very different, is the point. Yeah, so we'll experience this at some point. This is these are chaotic functions, and so chaos, if you've heard of that in terms of referencing math, well, hopefully we'll have a chance to look at that at some point this semester. But that's what that was supposed to. So my apologies. I must have just looked at it and thought, that's cool. I have to remember that if it's cool for me, it's nightmarish for you guys. So I apologize. All right, is there anything else though before we go on to linear? You had 2 sections, right? We had separable and linear. All right. Well, let's do linear then. That'll be fun. Do I have linear on here? What section? That was 2.3? I don't see 2.3. I'll need to, yeah, I think I need to, oh wait, here it is. Nope, that's not it. Yeah, I think I need to just, I didn't bring my book with me. Give me a sec so I can be talking intelligently about whatever it is that you have questions on. Give me a sec to pull up my ebook, which, because the publisher thinks I'm so cool, they give me access to the ebook. So actually it's because I made you guys buy the real book, which we know you bought the used version, hopefully. Okay, here it is. Ebook 6.3. Okay, so this one, now we went over the ideas from separable equations we talked about on Monday. Did we not? Or am I misremembering? Oh, I've got the wrong book here. Just a sec. Why did it give me the wrong book? Oh, okay, sorry. Let me try again. One more try. Come on. Okay, I finally found it. So you understood at least I think Zechariah was telling me that he was fine with the idea of separable equations. Hopefully you are as well. It was the execution, especially with some of those nasty integrals, that was the problem. But what about linear? Since we didn't go over this in class, you had the videos to watch. I don't even remember what the videos, I mean, I made those videos in summer of 2020. So yeah, that's why I looked so young. But I can't remember what what I did in the videos, but hopefully they were somewhat helpful. But what sorts of issues or questions? I think I think the reason why I chose the problems I did was because those were the problems that I had assigned on summer of 2020. And so I thought, well, if there are any homework, like I don't know if you noticed there were homework help videos that maybe they'd help. And so I just wanted to make sure that they lined up as best I could. Anyway, let's see if you have questions though about how to do the linear ones. And let's start with just like the 1 through 24. So there's like, I don't know if you have any bigger than 24, but try to restrict yourself to just 1 through 24 to begin with, and then we'll move on from there. So was there anything that we need to look at, Matthew? 11. We'll take a look at 11. Is there anything, well, let me look at it first and we'll see if there's anything in particular. So, well, this would be a good one, I guess, to illustrate what's going on. So just to make sure. So thank you. This will be a good one to illustrate like what's happening. So we have x dy over dx plus 4 is equal to x cubed minus x. So the idea, sorry, I forgot my y. The idea behind the linear differential equations is that you can take a linear differential equation and you can make manipulations to it so that it looks like you've got a product rule, and you are going to undo the product rule. So if you watched all the videos, like I said, 5 years ago basically, I don't remember how I covered that, but I'm guessing that I'm probably emphasized, because I like to emphasize the fact that linear differential equations are just undoing the product rule. So let us see if we can do that with this one. To do this, you need to first of all rewrite your differential equation, your linear differential equation, so that there is no coefficient of the dy over dx term. Sorry, I'm having trouble writing. Where's my, there it is, there. So this is going to be 4 over x, y, equals x squared minus 1. So let me explain what I did. I divided everything by x. That gave me 4 over x and gave me this. So far, so good? Seem all right? Next, we figure out our integrating factor. Integrating factor? Okay, hopefully you watched the videos and you caught that, but if not, here's what you do to find an integrating factor. You take the coefficient of y, so there's nothing in front of dy over dx now. You take this thing and you compute this. We're going to compute, this is the integrating factor. I'm trying to think what symbol was used. I'll just call it f for now. It was u? Oh, mu. Oh yeah, that makes sense. Yeah, okay, never mind. Get rid of f. Mu, thank you. So mu is going to be e to the integral of whatever their dx. What's that? Okay. Well, there was a car alarm that was going off incessantly this morning, and also during the previous class. So they aren't. It's not happening now, though. Maybe it'll start up again. We can only hope. Or maybe the battery died. Okay. Well, anyway, so there it is. There's the integrating factor. You want to know where this is? Well, like why? Okay, you can read the book. I mean, we could prove it. Do you really want me to prove this? No, you don't. You know, it's actually not bad to prove, but I'm not going to, because I want to spare you from that. But this, so yeah, if you you can read the book to see where this comes from, or watch the video. I don't know if I went over the derivation, but you always could fast forward past the derivation if you were watching the video, I suppose. So so this, think of it this way. This always works. Done. So you always want to use this. This will always work. And it's like magic. It's amazing. So in this case, my mu is going to be e to the 4 ln of x. So that's the antiderivative of 4 over x, is 4 ln of x. And then you're like, well, you know, what are we doing here with this 4 ln of x? Well, let me rewrite this. Anytime you have something like this, it's always best to move the coefficient of ln, move it inside the natural log. So use your rules of logarithms. And then we're going to multiply everything by this. So you have e to the ln of x to the fourth. Oh, sorry, one more step. My bad. Sorry, the whole point of that was to say that the ln and e are inverse functions, so this is just x to the fourth. Now we multiply everything by x to the fourth. Give me a sec. I'm just doing it this way so I can have different colors and make it look pretty. Okay, I'll just leave it like that. So far, so good? Okay, now let's just, let's finish this up. So we have x to the fourth. I'm going to call this y prime because I like it better. 4x cubed y is equal to x to the sixth minus x to the fourth. Now here's the magic. The magic is that if you do this right, then this function, its derivative will be right there. Isn't that amazing? Always works. If you do it right, always works that the function that is the coefficient of y prime has this as its derivative. And the reason why this is important is because if you take that x to the fourth, let's just do this down here, x to the fourth times y. What's the derivative of x to the fourth times y? We're going to use the product rule. The derivative of x to the fourth times y with respect to x is going to be 4x cubed y, derivative of the first thing times, don't mess with the second thing, plus the first thing times the derivative of the second thing. And that is exactly this. Isn't that amazing? I find it amazing every time. But now that you see that, all we have to do now is integrate both sides with respect to x. And when you integrate the left side with respect to x, we just get x to the fourth y. The right side, x to the seventh over 7 minus x to the fifth over 5 plus the constant of integration. And now let's just clean things up. Y is equal to x to the third over 7 minus x to the first over 5 plus c over x to the fourth. Done. Oh, was this an initial condition? Which one was this? What number? What, Matthew, what number was this? 11. Okay, yeah, no initial condition. But it does have a back of the book, so you can check the back of the book and this would be correct. I think that they're asking also for the interval where this is valid. And the only reason for that is because of this here. So, right, let me highlight. It's right there. It's highlighted in yellow. I was going to highlight it again. 4 over x. 4 over x means that the domain cannot include 0. So you have to pick. Is it going to be x greater than 0 or x less than 0? And why would we pick x greater than 0 over x less than 0? I guess it depends on initial conditions. But so I guess one such interval is that x is greater than 0. So the interval would be in 0 to infinity. Oh, yeah, you've got a problem here, too, with x equal to 0, don't you? So you don't want x equal to 0. All right. Yeah, it does say, yeah, determine the interval. So whenever it says, the largest interval over which that's not the largest interval. That it could be x less than 0 as well, right? As long as x doesn't equal 0. So who was it? Was it Matthew? You're the one? Yeah? That one look okay now? You know how to work through this? So it's good to have at least one example. So that was the easy example. Now let's deal with any of the hard examples. Were there any hard ones? I mean, you just get the integrating factor and then crank it in there. Well, let's go ahead and, yeah, we're behind, but I don't care. Let's go ahead and do this. This will be fun. Give you a sense of accomplishment. Just a minute. Let me just look. I want to make sure that it's not, there's nothing interesting. If it's interesting, I won't give it to you. Yeah, this, okay, that's boring up there. Okay, that one's pretty boring. Some of you might find number 2 just a little interesting, but not much. Okay. Here you go. Enjoy. Oops. Oh, well. There you are. I'll give you 2 more. How about there? Very nice. There you go. Oh, that's nice. Super. Here you are. Okay. Here. I've got a new technique for homework I'm going to try out. Let's try this out now. Differential equations. Oh, you've got both. Are these both? Yeah, they're both assignments. Huh. Well, okay. I can't use my new technique on the homework. I'll deal with it later. Hoping to just give it right back to you, but start that on Monday. Oh yeah, I got to get the quiz up here. So those who are watching on, I'll get it. So which is this one? It's 5. Looks like some of you are, it was boring. Was it boring enough? At least for some of you. You ready? Give it up. Take your time. All right. Yeah, he's good enough. He's happy. Yeah. Good job. Looks okay? All right. Thanks. I know you like to stare at it, don't you? Staring at it isn't going to make it any more right. It's as right as it can be. Oh, you got two of them. You didn't want to do two? Got something at least? Yeah. All right. Boring? It's boring. All right, hopefully we're coming down the home stretch. Those of you who are still enjoying the process. So. Oh, did you want me to take that stack? I don't want to take the stack, but I had a alternate way to deal with homework that I was thwarted because I did. Yeah, we'll start it on Monday. Not to worry. A couple more. You like it? It did. Is that good? Do you want me? Oh, we're gonna shuffle these. So can I put them in the middle, like this? See who else? You got one, Matt? You look good. Good job. All right. What do you think? You don't like this one? You have a. Let me see what you got. What's wrong with that? You don't have to solve it for y. Is that what you're trying to do? Yeah, just put a box around that. Yeah, you don't have to. It says if possible, give an explicit solution. You don't have to. I didn't. Okay, do I have them all? Any holdouts? All right, I'm going to staple them. Once they're stapled, there's no unstapling. Okay, let's take a look at what I've got. Hopefully I got them right. And hopefully they are, it's boring enough for you. Sorry, this isn't, there we go. Pinch and zoom. So here we go. First one, separate those variables. Get those y's on the left, get the x's on the right. They should never touch. You know, like the peas and corn on your plate as a child, or I don't know what it was that your hang up was. Now we're going to integrate both sides. Hopefully you can handle doing the integral of y squared is y cubed over 3, x to the 4th over 4. Look okay? Throw a c in there somewhere. And then let's figure out. Now, at this stage, by the way, I could solve for y. I didn't until the end. So either way works. You'll get the same answer. So I ended up doing this. I just, oh wait, what did I do? Oh, there, that. I said y is equal, what did it say? Y equals 1 when x equals 0? Is that what the initial condition was? And so that means c equals 1/3. Throw that 1/3 back in there. And then I thought, wait a minute, I've got to solve for y. So I multiplied everything by 3. That got rid of the 1/3 and turned it into a 1. 3/4, and then did the cube root of both sides. So you got this. That's supposed to be 3x to the 4th. I don't know why that 4 looks so low. How's that? So there's my. Yeah, that look okay? Did it right? Yeah, I don't know. I didn't glance at yours. So sometimes I look at yours and I think, oh, I made a mistake. I'll try to sneak up here and fix it before you can see. But anyway, getting back to this. Now this one, separate the variables again. Nice boring separation because that's a polynomial on the left-hand side. Sine of x, everyone knows how to deal with that. That's just going to be negative cosine. So, so this ends up being y cubed plus 5y on the left, negative cosine of x on the right. Throw a c in there. I've got this initial condition to deal with. Whoops, it didn't show up with, there we go. And so I'm just going to throw it in now. X equals pi when y equals 0. And so 0 is equal to negative cosine pi plus c. And you can hopefully do the math. C ends up being negative 1. And there's my final answer down there in the box. So what do you think? Did I make a mistake or did I do okay? Okay, hopefully I did it okay. So let me point you to one thing and then we'll call it a day and maybe we'll just take the whole weekend off. Give me a sec though. Let me find our Moodle page. Moodle differential. There we go. Of course, yeah, if you like those videos, I could post all of the videos from my summer school if you prefer, but I don't know that it's necessary. So where is it? Exams. That's what I wanted to show you. Is under exams, we now have practice exam 1. I know you're looking forward to the exam next Friday. And so there's the practice exam that you're going to want to look at. We can talk about this more next Wednesday maybe, but here you have a bunch of problems that are similar to some that might be on your exam. This is just classifying, like, are these ordinary or partial, linear or nonlinear, and what is the order? So you can deal with that. There's verifying solutions, finding explicit general solutions. There's some slope fields. Those look fun, don't they? And where are we? So I believe that we have done all of this. You could do all of it except for this one and this one. So you should be able to do this. I know you're looking, wait. No, that one is also, that one's in the same category as this. Sorry, I mislooked, I didn't see that. These. Wow, that one looks bad too. Oh, I see. I'm sorry. This is a different category. Determine if they're exact. Yeah, that we're going to go over on Monday. The exact equations. It was these I was thinking of. That this is linear. This is separable. You can do both of those now, hopefully. The last one, the bottom one, is called exact. So we'll talk about what that means on Monday. But so you could try. Well, I guess what I'm trying to point out is that if you do get bored this weekend because I didn't give you enough to do, and you're done playing all of your silly board games, you could always try a little bit of this. They're not silly, I know. I'm just kidding. Okay, so let's. I'm going to turn off the recording if you want to stick around and chat. Otherwise, hope you have a great